So there is actually this expression of why we need statistics, and it's a philosophical question, and only God knows the truth actually. Others must bring the data, right? So and now when we say the data, how much data and how like what type of data and so on. So uh, oh yeah, so the problem is that how much data we need, what type of data, and what type of model we are using to show something is true or something is not true. So, and the statistics is basically is the way to do that, and it's a science, So science of how to collect data, how to summarize the data, how to analyze the data, how to interpret the data, and how to communicate the data. So this is a science. And normally, where we start with the statistics, how we start. So statistics is a toolbox. In fact, we don't see say things like blindly. Normally, we start with a research question, which the research question first have like a primary outcome or secondary outcome or outcomes or a hypothesis, right? So normally we have a research question and we have some hypotheses. And then, okay, for that research question or that hypothesis, as we know, as I mentioned, only God knows the truth. So we need to bring the sample. The sample. So how we bring the sample? Then we need to say, okay, what type of study design I should have, right? So that's the other process. So we have a study design and then sample size. And as I mentioned, there will be a 2 days workshop in the spring that I will specifically focus on this part, but I'll show you a few things. And then once we have this study design, this sample size, this research question, the first things that we should start to talk about, what type of variable I do have. Do I have a quantitative variable or a qualitative variable? And you see, like I put this after the study design. If I studied, my design is longitudinal, then I will have probably longitudinal quantitative variables. Or I might have longitudinal qualitative variable. Right, so here depends on the type of the design that we have, and it is really important to first to identify what type of really variables I do have, and then when we identify the types of the variables, then we start to think about what type of analysis I'm going to do this. Am I going to do a like hypothesis testing, or association analysis, or modeling, or prediction? So you see, we go like step by step. And then what software I should use. So, and then what code I should use, right? So because there are so many ways of writing a code. Some codes are very time consuming. Some codes, specifically if you work with millions of data sets, like I have experience in R and in MATLAB specifically. Like I put a code in MATLAB, it took 30 hours, while the same code took in R like for 1 hour. So, and specifically R is very good in optimization. I have wrote a package about factor analysis, which I first thought that maybe MATLAB is very good at optimization. But then I realized that no, actually R is much faster and accurate in terms of the even optimization. So, and these are all called as SAP, Statistical Analysis Plan. So we need to have a good statistical analysis plan from our research question design up to what types of coding we are going to have. And here I'm going to discuss a little bit of study design. We have, generally speaking, these are like more applied in medical, but could be applied in animal and like other. We have cross-sectional data, design data collected as single time point. We have longitudinal data. Data is collected over the time. And we have, like, generally speaking, observational data. no intervention, just you observe things. So you don't intervene anything. And then we have this randomized trials. So basically, which is called as gold standard for many of the studies, if you want to see really the effect of something on something else. So this is called randomized trial. So choosing the right design is very, very important, because if we don't have a proper design, it might actually bias our results. And so this is, for instance, if you want to see the effect of age on cancer, basically you get like a couple of people in this first age group, second age group, and third, and then you compare them at one time. And basically you see, oh yes, the cancer was high in maybe in older group, right? So this is called as cross-sectional study. Just very briefly, in longitudinal study, you see like we examine the population over the time. So, for instance, one of the largest cohort in the world is in US, which is almost 120 years. And four of this, the project managers so far has been died because it's taking so long. And they are going to see really what impacts the human being life, actually. And somehow even US presidents are involved in this big project. Yeah. And randomized trial, as I mentioned, this is also a specific study. Normally, we have a target population. We have our inclusion exclusion criteria. We randomly select two types of group, intervention group, and the control group, and then we look at the outcome in those two groups. And this is a very, very rigorous group. And there are like several types of randomized trial, cluster randomized trial, and other types. And so I don't want to go them like specifically. So, and the second thing is, once we thought that what will be my design of a study, we need to specify what type of, like how many sample I need. Even if I am going to develop a prediction model, I need to know what sample size I do need to have stable results, okay? So it's very important because it impacts the statistical power and precision, and it will reduce the type 1 and type 2 error, and we will make sure that actually study is well powered, right? So as long as we have the questions, we know all those things. Now we come to the data summarization, how we do the summarization. As I mentioned, one approach is, like normally we have descriptive statistics, which is summarizing the data. So it is so easy, we all know. We go with mean, median, mode, etc. And then we go through the inferential statistics. So the inferential statistic you see is too much. So here we have hypothesis testing, model in relationship between variables. Sometimes we have mixed modeling, repeated measurements, survival analysis, time to event analysis. We have trajectory growth curve models. For instance, if you have certain types of tree and you want to know what overall how many types of hidden trees I do have in this population, based on their growth, Maybe one type of tree are sick, and we even didn't realize that based on the trajectories, based on the growth curve, right? So this is also another type of analysis. And it's called latent class analysis, generally speaking. And what we also have latent growth class analysis as well. We basically based on their growth. And at the end, we have this predictive analysis, which is called as the machine learning analysis. Okay, so you see that we have tools now, and more specifically, I am going to discuss basically the part that I thought that summarization is easy. So you all know. So basically, the hypothesis testing is somehow it shouldn't be very difficult. This is all of the statistical hypothesis testing graph that we have. Depending on as I mentioned, do we have a continuous variable or we have a discrete variable? And depending on the type of scenarios that we have, you see like there are several different types of statistical hypothesis testing that we have. And based on this graph, you can choose one of them and just proceed. And the R codes are really available for any types of statistical hypothesis text. So this graph shows almost everything here. So I won't go in the details. So you can refer to this graph and proceed with your any type of hypothesis testing, depending on what type of data that we do have. Okay, so this is the things that I wanted to show generally speaking. Now we are going to specialize specifically in modeling or association, which means both interpretation from the general linear model up to very complicated models like beta regression. So any questions so far? So what we discussed is basically general flow of statistical analysis. And like I showed you, always remember the GG gallery. You can basically develop any types of graph and for free. By the way, those who are not have not used R is also a free language, right? So, and it's very light. It's not like SAT. Okay, great. So let me move to this now to this part of advanced regression. So here we will cover a lot of things. Yeah, so basically you will be able to do linear regression model and advanced regression for categorical and count data, advanced regression for bound data and time to event data. And these are the outcomes that I'm hoping that you will have. And to also to choose a good model based on a given data sets. And also basically to discuss the explanation and also the prediction part and do modeling in R. So I guess after this slide, you will be able to almost model any type of data set that you have. Basically, you have a predictor variables or one or many, and you have like one outcome variable. So I have provided several tools that how you can basically model, and there are 7 examples from different ways. Yeah. So the general linear model, and we have first general linear model and generalized linear model. What is the difference between? So first of all, we assume that we have a sample size n. Here is the question, big question. What is the size? So I'm going to ask a question here from everyone. So if you have done a regression analysis, the first question that I would ask, how many samples do you think that is required for a typical, like a normal regression, not other? How many like sample? If someone like you can raise your hand or say, yeah, I think 20 observation or 100. So is there any number to say like how many variable like sample size is needed? Right. Let's say I have 10 variables, and my research question is to find if there is any association.
Yes, 25.
So 25, 30, 35 sample for 10 variables.
In each one.
So you mean like we should have 350 then? Okay. So you mean 335 observations per variable. Right. This is your rule of thumb, basically. Okay. What else? If does someone else has an idea? Yes, that's the good idea. In fact, I did normally when it comes to this type of studies, the first question I ask myself is, do I have enough sample size? Right? What if the samples are, because we all work with the real data and real problems. If we get underpowered, we will have problems. We said something that we might not be true. And sometimes we also don't want to waste the resources, right? If we really need like to have 100 samples. Why we have to have like 200 samples? And sometimes the samples are destructive, so like that this is the animal now like experiments, and many are trying to decrease the animal experiments. So one way is actually to use like power analysis, and more specifically, it's better to do a simulation study. Actually, I have run some simulation studies for different scenarios, and I compared with what we get from the simulation and what is the literature suggesting. And I suggest that if you have a specific, because the rule of thumbs of 220 observation per variable, and so on, are very typical, and they are for like general, they call as general rule of thumbs, even 35 or 20 or 50. So we don't know actually if they are good or not. So the best is basically to conduct this small simulation. In a small simulation, for instance, you know that your effect size is that much, and basically you simulate the data from the scenario that you think this is appropriate, and then see how much sample size is required. Okay, so I have done like one specific sample size, for instance, for logistic regression. Let me see if I have put this here, or maybe no. So yeah, so I'll come back to this point of how I have actually calculated the sample size. Let me see if my statistics is on. Maybe not. So I'll show you like how I do basically the sample size calculation for specific scenarios, and I'll be happy to also share that example with you. So here we have to be careful when we say sample size of n. The sample size should be enough. Okay, good. So yeah, normally we start with the sample size of n, and then we collect the samples. The samples are normally we have k predictor variables and one outcome variables, right? So and then we have x1, x2, xk, k variable, and then one outcome variable, and then maybe we have n, and then we will have a matrix, right? So as long as we have this matrix, normally in statistics we show the lower case for the observed values. So and we can call them as predictor, regressor, explanatory variable. Now, what's important is that the distribution of the predictor variables are not important for us, actually. So they could be categorical, continuous, or whatever. But if they are categorical, we should actually we should have enough sample size per category. If one category have 2 cows, then probably it won't be enough. We have to collapse some of the categories together. So nonetheless, we look at the response variable more. So what's important is the response variable or the y variable for us. And depending on that, we propose different types of regression analysis here, and also depending on the study design. If the study design is longitudinal, probably we should go to the mixed models, because there is a correlation between the observations, okay? Or we should use like some clustered approach. For instance, if you are going to use logistic regression, then there will be another way. So, but first we assume that the data is normally distributed. So this is the big assumption, but if the data is really normally distributed, then this is the general linear regression model, which we have like y equal to beta null plus beta 1 x1 plus beta k xk plus e. So which is the simplest model, but yet it could be very complicated. For instance, if there are coefficients if there is a correlation between the predictors, then what we should do? Or what if we have tons of variables? If we have, let's say, 100 variables, how to shrink down the number of variables and so on, right? So there are so many arguments here, but this is the simplest form. And this is a linear, as the name suggested, because for 1 unit increase in x1, for instance, y will increase beta 1 unit, even the other constant, other variables are constant. Was it correct? If we increase x1 1 unit, the y variable will increase beta 1 unit, given the other variables are constant. I interpret it like this. Was it correct?
Like beta 1 is 1.
Yeah, if I increase like x1, this one, 1 unit, the y variable will increase 1 unit, given the other covariates are fixed. We don't increase them. Was it correct?
If beta 1 is 1, yes.
No, yes. So was it correct?
And if beta 1 is equal to 1.
Yes. But
It's a correct question. I assume the answer is no.
yeah, exactly. How 99% of the people will say this is correct, while it is not actually correct. Do you know what does it mean? Let's say that we get the odds ratio of something of 4, or I got beta, as you mentioned, 1, right? So it means that if you increase x1 1 unit, y will be increased by 1 unit, given the other variables are constant. But this is not correct. The reason is that this beta 1 will have a standard, I mean, this in the estimation, once we estimated this one will have a standard deviation actually. It is not a fixed variable. What we say in statistics is that on average, y will be increased this much. You know, so we are going to discuss this a little bit deeply, but the thing is that for the interpretation is that whatever we got when we say x1, if x1 increase 1 unit, y will increase beta 1 unit, it is not correct. Y will be increased on average beta 1 unit. So for instance, you have seen that in medical journal, we have something called odds ratio, right? So odds ratio of smoking is 5 for lung cancer. But it doesn't mean that like if like whoever like smoke, he has 5 times more chance to get cancer compared to the
But then the model is reflecting that it would. So we now really solid distinguishing the response. But the model is still saying that it should increase all.
No, the model, because there is, you see, there is a random component here.
Yes.
Right?
But you don't have that into compensating when you apply model.
No, when we do model, basically, I will show you in a minute that, see, this is correct.
Yeah.
The expected value, okay? So the expected value of y, or the average of y, is this. So basically, when it comes to interpretation, as long as we are working with real data set, we should write that if we increase this one unit, that one will increase beta 1 unit in average. On average, that will be increased. So the average value will be increased beta 1 unit, not really the y variable. Because it means if we say that y will increase beta 1 unit, it means that for everyone, we will have the same variable. But it is not true. We have seen in the sample that everyone has not the same value, right? So the numbers are changing. What is true is that the expected value of y is equal to this one. Okay, so this is something that I have seen in many medical and agriculture journals that have been wrongly interpreted, actually. So and now here we see that this is the expectation is true, and also we have the standard deviation, the variance. If there is a correlation between these variables, the variance will not be true actually. So we will have the variance inflation factor. So mostly when we do this regression analysis, we should be aware about the variance between the predictor variables. If there is a variance or high variation, basically the results, the estimation, this part is okay, but the inference will not be okay. Okay, so this is the first point that we need to have in mind. And what if there is a variance between the variables, what we should do then? So one way is to actually to decrease the number of variables. For instance, we can have this VIF function, and from the VIF we can find the variables who have more than VIF of more than 5, and then we remove them, or more than 10. Some studies says more than 10. Or we go to something, another approach in statistics, which is called the ridge regression, which is not sensitive to actually to correlation between the variables. So we should use a ridge regression instead of linear regression in this form. Okay? So simply in linear regression, we have normality assumption, we have no correlation between predictors, and when it comes to interpretation, we should say y will increase, like the average increase or decrease, not the increase or decrease itself, because individuals are different. Okay, now before moving to the general linear model, I have one example, which is sounds like a toy example that I am going to show you, and basically how we do this in R. So example one, which is, so, you know, when you work with R, for those who are not familiar, basically we set a working directory or set WD. We use this set WD function or set working directory to show that my data is there. So now my data is in this folder. So I put like set WT, and then this is like job satisfaction data. So one beauty of statistics is that it doesn't matter we are working with job satisfaction, environmental factor, you know, like medical, etc. So the assumptions, the model is the same for all. We need to check the same assumption. If this is about job satisfaction, we do the same that we do for environmental modeling. So basically, the only change is the variables. And as I mentioned, we normally say y equal to beta null plus beta 1 x1, yada yada. So we don't care whether x is an environmental factor or a medical factor or a job satisfaction and so on. What's important is the distribution, okay? So, and the first things that we do is we check the distribution of the data. Okay, so this is how the distribution of the data. And in this data, you see, okay, the job satisfaction was from 50 to 100. And so this is my distribution. So first question, that because you might have done some regression modeling, does it look like the data is normal? Maybe yes, maybe no, right? So we can say from the visual actually assessment, we can say. So the best is to do a test, which is called as Shapiro test. So the Shapiro test will give us a p-value, which will indicate whether the data has normal distribution or not. So the p-value is 0.07, which means that the data has normal distribution. So we are fine. So we can do this regression modeling. And basically here I have done like a few things. For instance, the education level and the gender was factors. So let me show you the job satisfaction data set that I have here. For instance, the score for each person, like for the first one was a male, age was 53, and degree was doctoral, and job satisfaction was 93. Okay, so this is my data set. Now, since education and gender both were like factor variable, basically or categorical variable, I turn them to be factor. And when it comes to factor, we need to also say what is my reference category. So my reference category I put to be a master, and I'm comparing the PhD with master degrees. And for male and female, I put the reference to be female. So basically, so if once I did this, and then I have this data. So in basically, you see that I can still use the GLM function, but in the link, I put the Gaussian link or link equal to identity. And then we can see the summary of the data, the results here. So what I can see is that, yes, it sounds like you see that the reference was male. And now this is, oh, sorry, the reference was female. So sounds like males overall on average has have 7.5 unit higher job satisfaction compared to the female. That's how we interpret. So males are more satisfied with the job and significantly more than females actually. And age actually is associated negatively, means that those who are older, they are less satisfied with the job. And education, we could see that actually it's not important if first we look at the p-value. So actually in education, basically all level have similar job satisfaction. And you see, like for instance, it was 3 and 6, not much difference actually. Okay. So this is how we interpret this model, and also we have the general like a sigma variance of the model, which is 10. Error for this model is 10. So why this error is important? Because I can see that if I do a prediction from this model, what will be my error of the prediction? That's why we put normally sigma. If sigma was around very high, basically the prediction will not be very good. Now, imagine that now one question that we might have, and the structure that I'm putting here is the same for all models. So you have the data, you read the data, you estimate the model, you interpret, then you check the sigma for the model, and then you check if the model is adequate, means that, or if the model is good. What I mean by good is that if there is let's assume that you have a model with no variable, and you have a model with all variables. What's the difference? Does including more variable will improve the model or not, right? So for that, we use, yesterday we discussed the likelihood ratio test, and the likelihood ratio test is here, minus 2 times the likelihood of null model minus likelihood of the fitted model, basically. And here, this will gives us a sense that if the fitted model is significantly better than the model with no intercept, or the model with other like variables. Okay, so this is the general things, and basically in null model I have no variable. You see, like I have only intercept, and in the full model I have all variables. I had the full model before. So null model, and now I can print this deviance. So we see that the deviance was 13. It means that the model with certain variable, it has certain like the number is 13, means that the likelihood or the log likelihood of the model's difference between the two variables is 13 unit. Now, you know the AIC and BIC, and sometimes it's hard to compare with AIC and BIC. What if something that is shown there is by chance, happened by chance, right? So in statistics, we have this chance. And by chance means that what if you take another sample from this population? Might be we get something different result. So how we can generalize and how we can say that, yes, the model that I fit for this data with this 4 variables is adequate. We use this p-value actually. The p-value between the two models, the null model versus the full model. And the p-value is 0.01. So this one says that whatever we got above is actually good, because it shows that the full model, or the model that we fit to is significantly better than the model without any variable. Okay, so it means that our variables were somehow formative, or there was an effect from our variables, and overall the average effect of that was 13. But what we do, we have this p-value for that, and the p-value indicates that actually the full model was significantly better than having a null model. And basically, if there are some signals, you know that there are some variables that are may not important, while there are some variables that they are important in the full modeling. You can put those in the model, and basically you can generate similar p-values over there. So it's a typical example. And now I'm going to predict the job satisfaction of someone is female, age is 40, and the education level is bachelor. So I'm going to predict for this guy. So it just simply use the fitted model. Data is this, like gender level is female, age is 40, education is bachelor. Okay, job satisfaction will be 74. And we have this standard error here. The sigma was how much? 10. The sigma was 10. Basically, we can even make a 95% confidence interval for the job satisfaction of this guy. But our prediction was 74.78 for this for her satisfaction for the job. So it doesn't matter that the data is like, as I mentioned, this job satisfaction or whatever. So we proceed the same approach that we have it here. Okay, that's how we do basically the general linear model or linear regression models. So any questions so far? It should work as long as you have two models. As long as you have two models, it should work, and it should obtain their basically likelihood function. Because if we have a model, means that we have a distribution, and if we have a distribution, means that we can find the likelihood function after estimating the parameter. So the likelihood function basically will use that parameter, estimated parameter, we insert them and we can get them. And if some model does not, I mean, maybe some package does not, we can do it by R. We can do coding and we can calculate them. And we can see which model is better, in fact. So here it shows that the model that with all variables are actually significantly better than the model with no variable. And as I mentioned, you can check the model with two variable and another model with another variable and see which one is better representation of the data set. And you can see the p-value at the end. Okay, question. So what if we have 10 minutes or let me continue 3 more minutes and then we go to a break, okay? And then over there, I am trying to meanwhile to have your emails and to communicate the data and codes with you. You can also practice at the same time. Okay, so we covered this idea of, let me close this one so that doesn't appear again. Current tab, yeah. So we will move through the generalized linear model. So we understand how the linear model works and how we check the normality, how we check the goodness of fit. So generalized linear, actually general linear model was introduced. So let me show you the general linear model was introduced in 1896. 1896, very interesting, and the paper published in Philosophical Transaction of Royal Society, 1896, and then the generalized linear model actually born in 1972, almost 100 years later, the GLM born, and published, in fact, and again in the Royal Society, and but this time, instead of having let's say normal distribution, they assume that the outcome variable, you see I have put y, outcome variable, will have this exponential distribution basically, or exponential family. We have like a little bit open family. The normal distribution is closed, just one. But the generalized linear model is a big. So it can have normal distribution, it can have Poisson distribution, like it can have exponential distribution and other distributions, okay? So they introduced this distribution. But here, basically, if you remember, in the normal regression, we had expected value was beta null plus beta 1x1, yada, yada. But here, in the generalized linear model, we don't have the expected value. Rather, we have a function of expectation, will be beta null plus beta 1x1, etc. What does it mean? It means that if you increase x1 1 unit, on average, the G of XY will increase that unit. So this G will be depending on whether we are using Poisson distribution, binomial distribution, or geometric distribution, and so on. So we will be very specific on this G function. And you can see that the prediction, expected value of Y will be like this. So the expected value of Y, or the prediction. Again, it's good to know that when we say prediction, we say on average, his score will be this much. And this is the things for the AI people, like scientists. Don't say something with 100% accuracy. Actually, it's whatever you get for prediction, it says on average. And if you think that way, we don't fall in the trap of some bad misclassification, because we know that if we do this experiment from the same person another time, it might be changed, because there are so many factors affecting us, right? If you ask me some question today, I may give you one answer, but if you ask me this question 5 days later, if I am at night, really I can't even answer to that question, or it could be wrong actually. So what I am trying to say is that it's best to, when we report something, to cautiously report that, and report the standard error of that. So one reason that statisticians are actually generating the standard error is to show that nothing is 100% true. And there is a big word from Einstein. He says the only certainty in this world is uncertainty, actually. So nothing is certain. And specifically, if we are predicting like something more complicated, we shouldn't say with 100%. Because if you say 100% and if there is a contradiction, then no one will trust to that. Best is to say on average with this standard error, then it's fine. I'm writing a paper about ethics of AI now, and I mean, the main article came in the BMJ a few years ago, and they say people have the right to know. What does it mean? That they don't accept the black box? If we say someone will die tomorrow, there is no point of that, unless creating unnecessary stress. But if we say that the blood pressure is very high and probably he is a high risk, then there is a point on that. And what we can do, we can intervene and we can fix. So basically, the black box is nice, but we also should be aware of what's going on over there. And also, nowadays people talk a lot about the AI. What is missed is how accurate this AI. For instance, when you go and buy something from a market, it says, okay, this has this much of protein, carb, yada yada, and then you say, no, I don't like if it is too fat, too much fat, right? So you choose. What is the prediction models? Current prediction models is lacking in many fields is that people don't put a little bit, I mean, emphasize on the accuracy. Basically, this machine, the computer doesn't know. Whatever we ask, he will say something to us, right? So basically, we have to really carefully mention about the limitations and what are the inclusion criteria. What if the sample changed drastically? Do we get the same answer? Probably no. Okay. So yeah, so all is coming from this expected value of Y, right? On average, the prediction is this. But we don't know, but we can control this expected by what? By that standard error. So we got this standard error, then we will be fine. Yeah. So so this slide is about like the general linear model is a special case of generalized linear model, and basically we have the approximate maximum likelihood theory for the generalized linear model. The approximate, when I said the approximate likelihood function or the maximum likelihood, it means that we should have enough sample size, because we assume that the data, like the estimators, have normal distribution under some condition. One of the condition is that we have enough sample size. So therefore, we should check carefully the sample size, and normally the test that we do for the coefficient is called z-test with z-test. And you see the z-test is again coming from normal distribution, which might not be true always. And if the p-value is less than 5%, we say this coefficient is significant. And also, yeah, so there might be some cases that we use t-test or chi-square test for the coefficients. And the fitted model will look like this in the generalized linear model. And also we can estimate this, the sigma hat, to control the prediction, basically. Yeah. And basically, yeah, let me a little bit to be a bit fast. So here I was discussing mathematically, what if the variable that I have is a factor variable? How to interpret if the variable is a factor variable? I did that actually for the previous example. I mentioned, if you remember here, I mentioned that, I mean, in this estimate, this is the factor variables, right? So here we don't say for 1 unit increase in the gender, the outcome variable will be increased 7 units. We don't say like that. So we say that statement of 1 unit increase in X will increase Y, let's say beta 1 unit, if the variable is continuous. If the variable is discrete or factor, we don't say that. We say that males has on average 7.5 units higher job satisfaction compared to females. Okay, and we should do like this, so we don't say the other way. Why we do this? And in fact, mathematically we can prove this is the way that we do. So this is the mathematical proof of that. So yeah, I'm skipping this, and this is the prediction. So prediction for the general linear model and prediction for the generalized linear model. So now it's a good time to stop and then maybe have a break, and we maybe start at 10:30, and then we go to the example. Okay, thank you. Maybe we can stop recording. Yeah, so we are continuing with the oh, okay. So what we did so far is we had the general statistical roadmap. We went through the general statistical analysis, and we covered the regression with R code. We covered the interpretation. We covered the GLM overall, how it works, and what we consider for the GLM, how to interpret that. And you can see again, we I mean, nowadays everything is running around the prediction, but with the statistical approach like linear model or GLM, and I will show you a lot of nice approaches that we also have the prediction as well. So we have both estimation and we have both prediction too. So you'll see, for instance, linear model, and then we have this for the generalized linear model. Okay. Yeah. So basically, this is the code that we reviewed. You need to install this package to have this to check the normality assumption for the GLM for the linear model. And the Shapiro test. So we reviewed this part. We reviewed this. So now it's the time to go through the real GLM. Why we really do the GLM model if we have the linear model, right? So the problem is that sometimes the data is very much right skewed or left skewed. We are facing with some left skewed or very right skewed, and the data is not normally distributed. Now we are going to fix a problem here. What if the data is right skewed? What we should do in that case? Yet we are going to use the linear models, okay? So there is a transformation called Box-Cox transformation that is used to basically to transform a non-normal data to a normal data set, right? So if the data is very right skewed, then we have to do some sort of transformation. to convert data from normal to from non-normal to a normal, to a symmetric distribution. And that transformation is called Box-Cox transformation, and I'll show you how we do that. And when we did this Box-Cox own notation. So we say y. Now the transformed version of y will be y tilde. So you see that the new variable or the new observation is y tilde, and in fact the best formation to change the data distribution from a non-normal to have a normal. Because if we have the normal, then the interpretation is fine, the prediction is fine, and everything is in the good direction. So therefore, we need to have this transformation if the data is not normally distributed. So well, I have put some things here. Why, like, what if lambda equal to 0? What will happen to this? And I have proved that yes, if this lambda is equal to 0, this association will turn to be actually a logarithm of y. And you have seen maybe in some, like some of your practical applications that someone takes, take a natural logarithm of the data, then it will be fine, right? So you do this natural logarithm. Normally we do log transformation of the data set. And you see mathematically it's proven that we have the log transformation. And so these are some of the things that we have for the transformation. If I get the lambda, I mean, that these are the range of lambda, optimal lambda that the software will provide us. If the optimal range is this, normally we do this log transformation, the new variable is this. If the range of lambda is here, which we are going to see in the software, then we do this transformation, the new variable is this, and so on. You see, we have a bunch of actually criteria how to transform a non-normal data to a normal data set. Okay, so it's not a very unique. So these are some of the recommendations. And now, once we actually converted the data from non-normal to normal, then we have this nice actually interpretation here, but for the transformed version. If we x1 increase 1 unit, now we have the expected value of y tilde, or the decrease, not the original version. And the transform version is actually this. So you see that we have to be careful when we transform the data, then the interpretation will be different. And the prediction will be also different. Now the prediction is actually this. So you see that the prediction is now is coming from this association. So it's not like the previous one. Okay, and now so how we do this in R? Basically, we will have this library, this mass package, and then we do this Box-Cox transformation, and we get the best lambda and so on. So I have an example for that, and we go through that example. So the example about the house price, actually, the sold out price. But again, it doesn't, in statistics, all what I mentioned here so far, you see these are all X. This is the beauty of statistics and mathematical statistics. Basically, we say X. This X could be environmental factor, could be house price, could be age, could be sex, could be gender, could be anything, right? So we don't say X is this. So, and the statistician has the power to work with almost every discipline, because we have the umbrella, actually. So we have a big umbrella to work with everything. So I'm going to show you the second example here. This is the sold out set. You see that I have like continuous predictor, I have categorical predictor, and scales are different and so on. Okay, now let's see that how we can model and see the effect of different variables on housing like price, and also how to interpret and also how to predict. So we do two things: to see the effect, to see if the model is good, and then to predict, right? And have this. Okay. So normally I do kind of the data cleaning process. For instance, the price normally I divide it to like 10K to have a good scale, you know, the more readable. Or for instance, a square feet, I divide it by 1,000, because less than 1,000 is considered to be very like small, and more than one. So I'm changing the scale to be more readable, you know. So normally we don't need to say, oh, this is 600,000, 900, yada, yada, yada. We say 6.9 million, right? So for us, it's more readable. So yeah, so these are kind of air conditioning. I said the reference is no, and yeah. Again, look, this is the distribution of the outcome variable. Let me show you the distribution of the outcome. See? Okay, it looks like a bit like ugly, right? So it's not like a normal curve. And you see that we have some houses that are very expensive, and on the other hand, we have some houses that are cheap. So, and you see this scale is nicer than showing the 6 digits, basically. So yeah, so if we want to do normal regression, obviously it will be wrong, right? So because of the distribution. And again, we check the Shapiro-Wilk test normality. So we don't trust to the visual actually assessment. And the Shapiro test, you see, it says actually the data is not normal. The outcome is not normally distributed. Okay, what I do, again, I have this, as I mentioned, this mass package, and I do this Box-Cox transformation. You see, I have the Box-Cox function, and I put my outcome here, and then I will have my Box-Cox actually transformation here. And the Box-Cox is actually, it says the best value is, so here is the distribution of the, or let me show it here. So yeah, so here it shows that what value is the optimal value to change the data to be normal distribution. And it is -1 actually. So I have to actually convert the data from y to be y to the power -1. Okay, or to inverse my outcome variable because of this actually. And now, if I do this, you see the new price, the transformed price will be actually this one. So I do this, and then if I look again at this, now we could see that this looks like a normal now, normally distributed one. And now we do Shapiro test again. And now we got the p-value of 0.5. So in the past, it was not normal. Now it is normal. And now I do again. I do the modeling again. And you can see that, okay. So here are the important factors actually that are associated with the housing price. So we can see which one is important. For instance, this one, heating central. So the houses that have central heating, and this is very important because in fact I have a house in Canada and I know it's very important. And also this one is important. And the lot probably is important, but not that much actually important. And this one is a square feet. It tends to be, you know, like p-value of of 0.07. It kind of seems that this one is also tends to be important there. Yeah, one problem, with these types of looking at the p-values is that, well, if I set p-value of 5%, I get one result. If I set p-value of 10%, I'll get another result, right? So you see that p-value is a bit subjective. So recently, there are some statistical approaches like a lasso regression, for instance. Lasso, which really doesn't care about the p-value. It says whether a variable is important or not important. So, and it's coming from a different world. It doesn't care about the distribution and so on. But today we don't have that much time to go through the lasso. But this is the issue with the p-values. So if you set 10%, you get some sort of variables. If you set 5%, you get some sort of variables. But lasso regression will not have that issue. Okay. Nonetheless, this is now how we do this. So I fit the model, and again, I have the sigma for that. The sigma is this. Now, why the sigma is important? Because if we want to make a prediction, we look at this sigma of the model. Now, I want to check if the model is actually is adequate. What if the total model is not adequate, right? So we put the model without any variable, and we put the model with all variables. So here I am checking the full model versus a model with no variable, and I'm comparing these two. Basically, you can put a model with two variables, and then you can check the model with another two variables to see which one is better. But normally, first step in statistics, we check a model with zero variable versus a model with full variables to see if that makes sense. If the model with all variables is as equal as a model with no variable, it means that the variables are not very informative. So you see, I have put those, and then the likelihood difference is 43 units, which seems to be high. And then the p-value is actually very small. It means that the model is significant. The model that we did is significant. Now I'm going to predict. This is, for marketing. This is good maybe for those who are working in real estate. So, and maybe there is a one application in Sweden, but in Canada there is a house sigma. There is an application, and if you want to buy a house, it has estimated price for each house actually. And when you want to buy a house, you know what will be the estimated price. And this is the one that actually works for half sigma. And basically, if you want to see a 4-bedroom house with 2 bathrooms, square foot of this, central heating system is this, air conditioning is no, lot of 5, what will be the price for that? Okay, we got it. It will be like this one, and even I converted to the original price. It will be 658,000, the estimated price for that house. And I'm not that much worried because I now turned the distribution to normal, and if the data is normally distributed, all assumptions are good, and this price is valid, and I have the standard error for this. So yeah, this is the way that we work with the right skewed data. You saw that I first of all I showed that the data is not normally distributed. Then I check the box-Cox transformation, and what I did is I turned my data to be normal, and also I did inference and I did prediction. So we have everything now, right? Okay, good question so far. Yep.
The one of the questions is when we should apply transformation, because in general, I don't think we need the normal distribution of the response variable, but that the residuals are normally distributed. So maybe comment about that.
Yeah, sure. Basically, if the residuals are normally distributed, the y will be normally distributed. But principally, we look at the distribution of the outcome variable. I'm coming from that perspective. So if the outcome variable is normal, I mean, there is a little bit of mathematics. Let me show you in my pen here. So basically what we say is that the y variable has normal distribution, right, with x beta and sigma square. Sigma square. This is the principle of the actually normal distribution. We say y outcome variable has a normal distribution with this beta, x beta, with this average, and with this standard deviation. So this is coming from that perspective. But if y, like if residual has, I mean, so that is coming late actually. But the first things we check is the first thing about this normal regression is that we say y has this actually this distribution. See? So this is always true. And if you do that, we will get the same issue. If y has not normally distributed, then the residual will not be normally. Yeah, I mean that is a two-sided things, but if we look at the distribution of, yeah, sure.
Is that in the same units as we have in the input data, or is it for the transform domain?
Sigma.
Yeah.
Well, sigma is if we do sigma for the transform data, it means that that is for the transform data.
In this case, when you apply this transformation in the main function, does it basically?
So let me go back to the code.
Basically, you would have the back transform domain, like in the same as input, then you compare different transformations that to the sigma. But if you don't have that, like when I typically do linear regression, I apply the transformation myself to the data first, and then I need to apply the back transformation and the correctional transformation bias in order to compare the outcomes of different models. But when you do it in RAM, is that already dealt with, as I understand, with the main function, but that also holds for the sigma?
Yeah, I mean, when we do, let me show you my code here. If I understand your question like correctly, so you see like I have fitted model, right? The fitted model is the transformed, you see transformed price, TR. And now I have the sigma for the fitted model. Okay, so basically, I mean, for the new model. You can have it for the previous model as well. So basically, but what's important, I mean, what's the use of the sigma is the application of the sigma is for the prediction. If we want to predict, and basically we can see how much like error we are expecting. Yeah.
In this example, you still use the identity function, but if you would use it for clean function, what is the sigma representing then?
So I'll come back there. I'll go back here. So basically, when I do this transformation, because I transform the data to be normal, basically I use identity and I use the Gaussian distribution because I have shown here that the data is Gaussian, right? So basically, even though I am using the GLM, but it's really a linear model, right? Because a linear model is a special case of GLM model if the data is Gaussian and the link is identity. So I'll have another example now. I'm going to describe the gamma regression. Over there, we will have another thing. Okay, another question maybe. No. Okay. Yeah. Yeah, last regression. Yeah, so if you want to select the variables, normally it is going to be for variable selection and also estimation. It selects the variable and also it estimates their effect. So now you see like now here we look at the p-values and we select or deselect. But this could be a little bit problematic in two ways. One is we assume that the coefficients are normally distributed, which really might not be the case. The other issue is that it depends on the p-values, okay? So if you assume p-value of, let's say, 5%, you got one sort of variables. If we assume p-value of 10%, we expect to see another variables. Now, okay, which one is true? But lasso doesn't care about the p-value. It has a different procedure actually, and basically it will says yes or no. Variable is selected or not selected. So yeah. Okay, so we discussed this part, and we saw how we apply it in real data, the box-Cox transformation. And this is the predicted value after box-Cox transformation. So you know why we do this box-Cox transformation? That's one thing some people could ask. Because when we do the box-Cox transformation, if we can turn it to a simple linear regression or multiple regression, then the job is actually way easier than other approaches. You know, we could go through very complicated models like gamma regression and so on. But if we can do it here, it's nice. On the other hand, if the data has 0 on their scale, then we cannot do like gamma regression. So the GLM family, like gamma regression, assume that the data is positive. Some people add like 0.001 for the data set and to make it positive, but we added something, right? So 0 is really different than 0.01. So if I don't buy something, it's different than say, yeah, I bought something, right? Even with small probability. So basically, that's why I don't recommend sometimes to add even like that. So because what if you haven't bought anything? Okay, we discussed this. Okay, see, this is the gamma regression that is specifically designed for right-skewed outcome variables if there is no 0. If there is no 0. So gamma regression, in fact, and I have worked with gamma regression, and I have fit this for the prostate cancer dataset. And my best published paper was about the gamma regression. So the story is that there was a paper in a very high journal, and then they used to see what are the main cause of prostate cancer. And they assumed the data is normally distributed, but then it turned out to be that the data was not normally distributed, and it was actually distribution was gamma. So I started making the story from that, and then I wrote a paper from with my master student, and she just defended her PhD a few days ago in Jönköping University. So yeah, so the gamma distribution is specifically, or gamma regression specifically designed for right-skewed outcome variables. And so why, one may ask why we always don't transform the right-skewed data to normal. Because there is a variance component. If the variance is not constant, we cannot make it actually normal distribution. So it's not just about the distribution of the data, it's also about the constant variance. So gamma distribution basically in generalized linear model, the variance function is a function of the average. Okay. So basically, that's the reason that sometimes we have to choose gamma regression. Okay, this is the form of the gamma distribution. And this is, again, it is specifically designed for right-skewed data. And when the basically variance is not constant, we assume that in the linear model, gamma is variance is constant, but there might be the case that the variance is not constant. In that case, we have to move to gamma regression. Yeah, and in gamma regression, the expected value of y is like this. We do some sorts of transformation, but at the end, it's a kind of the log of expected value is a linear function. Yeah, so and the predicted value will be expected value of y, or the average of y will be e to the power beta naught plus beta 1 x1, etc. So it's not like we have this exponential function here. So we need to be careful when we interpret this. And we have the dispersion parameter as well. And the dispersion parameter is about the constant variance. And basically, how we interpret this for 1 unit increase in the outcome variable, the response variable, the log of the expected value will change 1 unit. Okay, so the log of the expected value will change, not the expected value. So if you increase, for instance, age 1 year, we say the log of prostate level will increase this much. So it means that the original prostate level will increase exponentially, actually. So sometimes the case that if you increase things 1 unit, when people are getting very old, like let's say 80 or even more, for them, one small cold is actually a big issue. But if someone is, let's say, 16 years old or 30, 40, a cold is nothing, right? So we could see that it's not a linear. So we have sometimes an exponential issues. Yeah, I'm sometimes skipping those. So let me go through the third example, which is about the fourth example maybe, which is about the gamma regression. This is not about, this is progress regression. Let me go back to the other one. Yeah. Yeah. So this is the gamma regression. So in gamma regression, again, like we do the same procedure for the housing price, that the response variable was skewed. And then if we want to do gamma regression for that, basically we use the GLM function, and this procedure is the same, except we in the family we put gamma, and the link is the log link. So this is the gamma, and then now we could see that which variables are important or which variables are not important. Again, we could see, yes. So what's important here is the square feet and central, like heating system, and AC. So if you remember in the previous one, the p-value was for the square feet of the house was 0.07, right? So if you remember, I said, okay, it's a bit suspicious, and what if we do 10%? So when we do gamma regression, actually we got p-value of 0.02. And principally, the square feet of the house is important, we think, right? So because we have more land and it should be expensive. So now the question is, should I fit the normal regression with that log transformation, or should I fit gamma regression? This is the question that we can easily answer by likelihood function. We can see that which one, gamma or normal, has a better fit to our data set, actually. And from there, we can see really like which one is I mean, this was the part that was suspicious, right? So square feet of the house, because over there it was 0.07, now it is 0.02, the same data set. But our assumption is that, I mean, generally speaking, we know we all have house. Bigger apartment and bigger house are more expensive. And we got it from the gamma regression, but maybe not from even the normal regression. So yeah, so basically, first of all, we do check the null and so the deviance. So here you see this is like 45 unit, and I guess in the previous one it was 43 unit in the normal. So when we fit like gamma distribution, we got a little bit better actually likelihood function. So it means that gamma has better fit for this data set, even though we turn that to the boxcock, etc., to the normal. But at the end of the day, it sounds like gamma has a better fit because the likelihood with gamma actually is better. It's at least 2 units better. So which model we should trust more? Probably gamma model is better for that. And when it comes to the prediction, I guess this was this, yeah. So basically the prediction, and then let's see, the prediction is 673,000 for this house with this characteristics. Yeah. So this is how we deal with the gamma regression. So we saw the distribution, we fit the model, we look at whether this is adequate or not, and then we do a prediction. So basically we have almost everything. So time is flying, and my expectation was to go through many models, but now I only covered the normal, gamma, and so on, and yet it's 11:15. So maybe I go through like 11:30, and then you practice a bit, right? So let me show some more models. Okay. Yeah, so we discussed this. So now I'm moving through the binary response variable. Here I will be more flexible because my assumption is that most of you are very familiar with logistic regression. It's easy, but I'll go through the hard, like with complex models. So yeah, binary variables, the answer is 0, 1, pass or fail or whatever. The outcome variable is 0 and 1. The one reason that I am looking at the outcome is very consistent across all models. So we pass the outcome variable of continuous, which was either like a normal, or we transform, or we go through the gamma. There is a specific one which is bounded. I'll cover at the end, which is beta regression. If we didn't have the chance to cover that, just please remember that if the outcome variable is bounded or proportion, we will use beta regression. It's something new. It was born in 2014, and yeah, I have a recent paper published on beta regression too. So yeah, so binary outcome. So normally we use logistic regression, probit regression. Oh, sorry, I have to answer. Oh, wait. Yeah, logistic, probit, or log models or complementary models. So these are the types of models that we normally use for the bounded outcome variable. But the most common one is the logistic regression and also probit regression. So in the logistic regression, they basically the expected value of y. So beside the basically the estimators, the expected value of y, or the prediction is this actually. So this is the form of the mathematical form of the predictor variables. And it's actually introduced by Cox in 1958 in the Journal of Royal Society. So it's one of the most cited approach in statistics, binary logistic regression. And yes, we have the logit function. The form of the regression is like this. So logit of p, or logarithm of the p, is a function of the predictor variables. And it means that for 1 unit increase in x, let's say x in the level of x, the log of p divided by 1 minus p will increase beta 1 unit. Or in the other one, on the other hand, I mean, the p hat is this, so the prediction is this, and we have something called the odds ratio here. So basically, the odds ratio is showing. So let's assume that you have two groups of people. One is smoking, and one is not smoking, and we have cancerous, non-cancerous. Normally, we report the odds ratio of smoke for cancer. And it means that those who are smoking, how likely they are getting cancer compared to those who are not smoking, on average again. Yeah, this is the prediction. And in the probit model, basically, so I don't want to go to the example of logistic regression because you have. I'm just introducing some other models like probit. In the probit model, the outcome variable is p, but it is a function of a normal function of the predictor variables. It's like this, and the prediction is also a bit different. So here, yeah, basically, the one beauty of the probit regression is that we say for a numeric predictor like x, the estimated coefficient, or beta 1, let's say, or beta at 1, gives the change in the estimated z score of the response variable. Okay, so the difference is a bit I mean, it's a bit different than the logistic regression. We say the estimated z score of the response variable. Okay, so not the odds ratio, the z score. Some journals or some people are interested to see the score. I mean, the change in the z scores. That's important. But if they want to, we do this probit regression, and this is the prediction. Our implementation. I'm skipping this part. Now, 0, 1 was one typical outcome. If the outcome is yes, no, 0, 1, etc. But then we have another types of outcome, which is called as a count. You go to fishing, you might get 0 fish, 1, 2, 3, etc. Right? So these are called as the count variable. For count variable, normally we have Poisson or we have negative binomial. So this is the distribution of the counts. Could be Poisson, could be negative binomial, or could be zero inflated. If I don't go to fishing, I will not catch any fish, right? So in that case, there will be many zeros. And these models will be like two parts models. So we'll go through those. Yeah, so in Poisson regression, again, we assume that the outcome is 0, 1, 2, 3. Now here, if we know that the outcome variables always start from 1, then it will be truncated Poisson. Normally, the textbooks doesn't cover that. Or if we know that the outcome variable is between A to B, we know that we get at least 2 fish and at most 5 fish. Basically, we have another form of truncated distribution. So we should be careful about that. This is the form of the Poisson, and this is the predicted variables, and so on. So I'm skipping those. It's easy. Many of you probably knows that. And yeah, so zero truncated Poisson regression. Sometimes what we have is that we know the outcome variable is not 0. It is at least 1, 1, 2, 3. So in that case, we should use something called truncated Poisson distribution or truncated Poisson regression. And for the truncated Poisson, actually the distribution has this form, this transformation. But the expected value of y, you see, this actually is a nonlinear now. It's not a linear model. It's a nonlinear. You see, there is a different form for the expected value of y. And yeah, and when it comes to basically to the prediction, we have this lambda of this form. And yeah, so the prediction, when you have, let's say, a new predictor, you want to make a prediction for future, mathematically prediction will have this formula. You know, sometimes it would be nice to put the mathematical expression for your prediction so that the readers also know that how you predict this. I learned mathematics from really my mother, and she was showing the mathematics by just fingers. And that's why I become very big fan of mathematics. I saw that how simple it is. And sometimes if we show that how we make this prediction, not like a black box, people will like it more. And I say, yeah, if you have a truncated Poisson, if you estimate these betas and you put your x's, this will be your outcome. Yeah, so for basically for implementation, we will use the VGLM function in R, actually, for the truncated Poisson. It's not GLM, it's VGLM function in R to do this actually vector generalized linear models. We will use those for the truncated models or Poisson models. Yeah, I have examples, so you will see the slides. We have less time, so yeah, so now, so we discussed the idea of truncated Poisson, but then we have a zero inflation. So sometimes we saw many zeros in our data set, in our outcome variable. It means that, typically in Poisson distribution, we know like how many zeros we are expecting because we know the distribution of the data, right? So you can use R and you can estimate that how many zeros you expect. And if you saw a scenario that there are so many zeros in the data set, you got suspicious that, oh, actually, there might be some things and the data is zero inflated. So if their data is zero inflated, and I have examples, then basically we will use zero inflated Poisson regression. And the zero inflated Poisson regression has two parts. One part is explaining why we have zeros. And basically another part is explaining why we have ones. Okay, so you see that this model has two parts. Basically, one is for zeros, one model for zeros specifically, and one model for the positive response. So an interpretation also is different. And you see that the prediction also is different. Some predictors will explain why we don't go to fishing. Some explains if we go fishing, what will be the most effective way of fishing actually to get more fish. Okay, so we have like two parts models, and this is the prediction actually. So we have two parts again for the prediction, and the expected value of y generally is 1 minus pi times lambda. So I guess that now, and again, so this is the final form of the predicted prediction. If we estimate everything, we can even do the prediction by hand. It won't be so hard. So we have betas. The betas are coming from model or coming from model. We will insert the predictors, and then we will get the prediction for the scenario. Okay, the climate condition is this. This is my fishing characteristics. how many fish I would expect to get. So I can get it. Yeah, for implementation, we will use like a zero inflated function, and then we can get that regression done in R. So there is an example here. So and then we have like basically harder models for the zero inflation, and the harder models is a bit different than the Poisson model. Yeah, so let me see what else we have. And the harder models is coming from this harder function in R. So we do with that. Yeah, then we have the regression for the over dispersed data set. Over dispersed, so in Poisson distribution, the assumption is that the variance is actually equal to the mean. Variance and mean are equal. If you have a data, and the first things that we measure to see if should I use over dispersed model or Poisson simple model, I look at the variance. Sometimes this is the case that the variance is very bigger than the mean of the data or of the response. In that case, we could use, there is over dispersion, and we should use like negative binomial. And similar to Poisson, we have negative binomial, zero truncated negative binomial, zero inflated negative binomial, and harder negative binomial models. So it's getting more and more funny and complicated. Yeah, so these are some of the forms for those, basically. And basically for the negative binomial, we use like the GLM negative binomial function in R to see like what factors are important versus what factors are not important. For the zero inflated negative binomial, we have this form. I'm getting a bit quick. And this is the prediction. And again, in our implementation, we have zero inflated, and we set the data will be, okay, negative binomial. Yeah, so we get it. And now for the proportion response, when the outcome variables is proportion. So sometimes your outcome is proportion. You see the proportion of the female, the proportion of this. So anything. So if the outcome variable is proportion, it means that your outcome variable is bounded between 0 to 1. The proportion cannot be less than 0 and cannot go beyond 1. So it's not optimal to use linear regression, in fact, because linear regression has different assumptions. So in that case, we should use beta regression, actually. And we have also a zero inflated beta regression, one inflated beta regression, and different types of beta regression. But yeah, so the beta regression has overall this form, and the location parameter is this. So we can skip some of the parts, and the prediction is this. Well, and in R we use the beta reg function or beta reg package to do beta regression. So I'm giving you the keywords. It's a bit tight time to go through all of them. Yeah, so we use beta regression when the outcome variable is either proportion or the outcome variable is bounded between A to B, let's say. We use beta regression. We have, and then what if I get many zeros? So proportion, if there are some situation that we get many zeros for the proportion. And in that case, we can use zero inflated beta regression as well. And yeah, so we have those here, like estimation, prediction. And for that, we will use GAMLS, GAMLLS package to fit zero inflated. Yep, so we covered And we saw there are so many tools to model the data set depending on what type of outcome variable we have. If the outcome could be continuous, could be discrete, could be zero inflated, could be bounded. We have all tools here. But when it comes to like model selection, so we can think about which model should we use. So one approach was to look at the likelihood function. The other approach is to look at the RMSE, the root mean square error. If you want to predict, you get prediction from one set of the data, one model, and you can get prediction from another model. The model that has lower RMSE, that one is better. Yeah, and sometimes there is a bit of basically the complex models might have better performance, but if you have so many parameters, then they will catch all possible patterns in the training data. But when it comes to prediction, they might not be very good. So there is this bias variance trade-off issue. So basically, what it tells is that we need to make a balance between the complexity of the model and the interpretability of that. If we set 100 parameters, yes, we can get zero error actually, but it will not be the optimal way. If we go to testing data, then it won't work that much well. So, and this is about the AI, and specifically when people do training and testing, if training and testing are really we do it, something we do is we do like 70%, 30%, something like that. But if we do this really randomly, it means that the whole population is the same. But basically, we do internal validation. It's not a very external validation. So what I'm trying to say is that even though if you do training and testing, the data is very similar to the original population. It's coming from the original population. It's best to do some sort of external validation as well, not really rely on the external validation. And in terms of the model selection, AIC is one of the good one. BIC, trusted R square is like, okay, if you want to select variables, maybe you could use like stepwise regression, and step AIC function is here. And there are some packages in R that also can do the variable selection for you. For instance, the train function that can do that job for you. Yeah, so that's all for me. So because now it's just 20 minutes we have, what is the best could be is look at, generally speaking, to the examples, to the data set, and yep. Yeah, okay, perfect. So yeah, so basically you can now start to install the package and working all those, and you can practice and see how it works. Okay, great. Now, yeah.